Before starting, let me start the recording. Bismillahirrahmanirrahim. Okay, dear students, last time we were discussing design of plate girder, and until now what we have covered, so we have already learned how to proportion the plate girder. So what is the proportioning of plate girder? It means that deciding the size of web and flange, which are based upon bending moment. So actually, the first of all, what we do, we select the height of plate, which is also the function of bending moment diagram, and then we decide the thickness of plate girder. We are having three different criteria, and then we decide the size of flange, which is also depending upon moment. So what we have discussed in proportioning of plate girder, we did not design the plate girder or proportion the plate girder based upon applied shear force, or we did not. We only satisfy the shear force criteria in deciding thickness of web. And we have also discussed that in plate girder, our flange may be compact or they may be non-compact. So when we check the moment carrying capacity of plate girder, so if it is more than applied bending moment, then our section is okay. Okay, next phase is design of stiffeners. So what are the stiffeners? These are vertical plate or transversal plate which are provided along the length at suitable distance. So A will be the spacing between the stiffener and H is the height of web. So first of all, we need to discuss why we need to provide the stiffener and what are different type of the stiffener that we can design for a plate girder. So when we proportion the plate girder, so we also satisfied one condition that our web must be cylinder. What does it mean? That the height of the web over thickness of the web ratio should be more than lambda R value. Lambda R value which was 161.2 for 830/60. This means that if our web is cylinder, it means that our web will, the plate girder web will always undergo elastic buckling. Elastic buckling means that the web will buckle at a stress value much lesser than yield value. So if it is buckling at a stress value much lesser than yield value, it means that our web buckling strength will be very less. So what we need to do, if we check the capacity of the web only without any stiffener. If the shear capacity of the web is more than applied force, which applied force, for example, in example number 6.1, when we design the plate girder, so we plotted the shear force and bending moment diagram. So this was the bending moment diagram. So maximum shear force which is acting in a plate girder for this loading is 1519. So what we do, we will check web. If shear capacity is more than 1590 in this case, then we do not need any stiffener. But if the capacity of plate girder web is less than the applied shear, it means that we need to strengthen web. And how we can strengthen the web or improve shear capacity, we need to provide the stiffener, or we need to subdivide the web panel into different segments. So we in stiffener design, what we are supposed to do, we are going to decide what would be the spacing of stiffener, number one, and what would be the thickness of stiffener, because length of the stiffener is already known. So stiffener is provided between the flanges. So the whatever is the height of the web, same would be the length of stiffener. So when we are designing the stiffener, so what is the designing of stiffener mean? What would be the spacing of the stiffener and what would be the thickness of the stiffener in such a way that the shear capacity of the web panel may be more than applied shear force. So here, first of all, I will give you the overview of the stiffener and what type of the stiffener are there and what are design criterion. So it is usually necessary to stiffen the thin web of plate girder to prevent loss of strength due to web buckling. So how the strength is lost? Because if the web is cylinder, then we are unable to achieve full strength of material. For example, if the yield strength is 250 megapascal, so the web will buckle before the applied stress will approach to 250. Rather, the web may buckle at a stress value 100 megapascal. So it means that we are losing or we are losing 150 megapascal reserve capacity because web is buckling before the stress approaches to yield value. So what type of this stiffener and how we can provide this stiffener? For riveted or bolted type of the plate welder, usually we are using angle section. What we do, the one side of the angle section is fastened or riveted with the web and other leg is projected. But if we are using the welded plate welder, so simply we need to use a single plate that we can weld with the web. And weld is provided also with the web and also along the stiffener that we will discuss in detail. So how many type of the stiffener are there? Actually, basically based upon, depending upon the applied load and design behavior, we are having two types of stiffener. Number one is called bearing stiffener and second is intermediate stiffener. So we shall learn design of both type of stiffener. But in today's topic, we are particularly studying the design behavior of intermediate stiffener. What are the bearing stiffener? So from the word bearing, bearing means that they are bearing or resisting the load. So bearing stiffener normally they are provided if wherever a concentrated or a very heavy force is acting on the plate girder. So what are the type of the concentrated force? Force reaction and any heavy or concentrated load which is acting on the plate girder. So we are always providing the bearing stiffener at sport and wherever point load is acting. Why? Because when a concentrated or a very heavy point load is acting, maybe or on any side of the flange, so actually due to the stress concentration, it may cause web crushing or web crippling. So to safely transfer the force from the top or bottom flange to the web, so we need to increase the area of the web by providing the bearing stiffener. So these transfer heavy reaction or concentrated load to the full depth of web, providing a uniform shear transfer. So they change the stress from local to the uniform distribution. So there will be no crushing or web buckling will occur. So bearing stiffener are always provided in pairs. In pair means they are provided on both sides of the web. So for example, we have discussed this example 6.1. So here you will see that the force or end reaction, these are also the concentrated force, so very heavy force, 1519, which is acting at the end. And moreover, this plate girder is also subjected to concentrated force, 750 kilonewton. So this force is only acting on a very small region. So what would be the source of this 750 kilonewton? That may be the end reaction of secondary beam. Maybe the secondary beam, it is resting at this point on the plate girder. So end reaction of secondary beam, it may serve as a point force. So it means that from the top at point B and C, there are chances that the web may cripple or the local crushing may occur due to the a heavy force. Similarly, due to heavy force reaction, which is acting at the bottom phase, so the web from the bottom flange, it may crush or it may cripple or it may buckle. So we need to provide bearing stiffener at point A, B, C, and D because these points are subjected to concentrated force. So it means that location of bearing stiffener is already known. Wherever the force reactions are coming or heavy load, they are being transferred to the web, we need to provide bearing stiffener. So this way, last time when we designed this plate girder, so it means that we already know the location of bearing stiffener. So bearing stiffeners are provided at the end and underneath concentrated load. And then in between this panel, if the shear capacity of the panel between the bearing stiffener is less than applied shear, then we also need to provide the intermediate stiffener to enhance shear capacity of web. So bearing stiffener, they serve as both as an intermediate stiffener and as a bearing stiffener. Bearing stiffener means that they are also increasing shear strength of the web, and they are also resisting the applied or concentrated force by providing column action, because bearing stiffener between the flange it may behave as a column, and we shall discuss in detail in our next topic. And what are intermediate stiffener? Intermediate stiffener are also called non-bearing or stability stiffener. These are these stiffener are not resisting any applied load. Rather, they are stabilizing the web, or they are improving the shear capacity of the web. And these are placed at various interval along web to counteract against the buckling due to diagonal compression. So I will explain this phenomena. But at the moment, you must understand intermediate stiffener, they are provided to enhance the shear capacity of web or to stabilize web. So we need to decide what would be this spacing of stiffener and what would be the size of stiffener. So here you can see that these are the type of the bearing stiffener, these two, and these are provided above this force reaction, because at sport very heavy load is acting. So there is a chances that web nearby this force it may crush locally. So it means that to increase the area of web, we are providing stiffener. So here you will see that bearing stiffener, it may be comprised of one single plate on one side, or we may provide the combination of various plates. It depends upon applied forces. So here you can see that bearing stiffener is comprised of seven plates, one, two, three, four, five, six, seven. Seven plates on one side and seven plates they are provided on the other side of the web. Why they have decided the seven bearing plates? Because the bearing plate, the number of the bearing plate and the size of the bearing plate is based upon applied shear. Maybe at this reaction, applied shear force or that this end reaction is very heavy or very large. You can see that these are two separate plate girders. They are discontinued over here, and bearing section is comprised of two angles on one side, and one double angle is also provided on the other side. And here these are the intermediate stiffener. And intermediate stiffener, normally they are provided at constant spacing along the length. And their function is not to resist applied concentrated force, just to stabilize the web. So normally intermediate stiffener, they are only provided on one side or in alternative. Alternative means if this stiffener is provided on this side, and this stiffener will be provided on the other side. So this stiffener, one stiffener on the one side of the web panel, or one stiffener will be on the other side, or all stiffener, intermediate stiffener on one side of panel. Okay, here, uh, before explaining this, let me explain you this equation. Actually, how we can determine shear capacity of web. So normally shear capacity of web is equal to shear strength of web material into area of web. So that is the area of web. So actually we know that web is cylinder, Web slender mean that slenderness ratio of the web is more than lambda R value of web. It means that our web will never be fail due to yielding of the web. So web will never fail due to shear yielding. Rather, the web will buckle at a value much less than the tau y or much less than the fy. So what we are doing, we are using a parameter which is called CV value, which is the web buckling coefficient. So this web buckling coefficient is the parameter which is converting the yield stress to the critical stress or buckling stress. So CV value is the ratio between critical buckling strength over yielding strength. So tau critical for a slender web will always be much less than tau y. So what is that value? If we are multiplying these tau critical with the CV, tau y with CV, so we may have tau critical. So similarly, that will also be equal to critical buckling strength, shear force, or the capacity, shear buckling strength over yielding shear strength. Because tau critical multiplied by area of the web is equal to VCR. So area of the web on the top and bottom will be same, so they will be discontinuous. So here CV prime is the, you can say, a coefficient which is used to convert the yield strength to the buckling strength of the web, or that is a parameter that is used to determine the shear capacity or buckling strength of web alone without stiffness. So forget about this CV prime. So because at for the time being, or in our previous topic beam design, we are considering only this formula tau y into area of the web into CV, and CV value is equal to 1 if height of the web over thickness of the web is less than 62 2.4. If you remember, that was only for hot rolled section. But if we are providing the stiffness, if we provide the stiffness, then we have some extra strength available, which can be determined by CV prime. So CV prime is the shear enhancement factor. In other words, this is not the exact definition. So CV prime is the strength or shear strength improvement in shear strength due to stiffness. So the increase in shear strength by the provision of stiffener is computed by CV prime value. So the total strength will be equal to, because this parameter is constant, because tau y is equal to 60% of Fy, because shear strength of steel is indirectly determined by multiplying tensile strength with zero point 0.6, and area of the web is height of the web into thickness of the web. So this CV is the factor which is used to determine the buckling strength of web alone without stiffness. And CV prime is the factor or which let us know the improvement of shear strength by providing intermediate stiffness, or increase in shear strength of web due to provision of intermediate stiffness, and how we are having extra strength available due to the stiffness we shall discuss in our today's lecture. So one thing is I will explain after I will come back to this question and I will explain. So let's suppose we are having a beam. First, you need to understand that is a complex phenomenon. Actually, you shall discuss this topic in detail in sixth semester structural mechanics. But I would maybe give you an overview, the behavior of the web when it is subjected to shear forces. So you know that if we are having any beam which is subjected to any type of load, so the shear stresses, they will be maximum along neutral axis, and they will also be maximum where applied shear force is maximum. So let's suppose if I'm taking a very small element from the web or along the neutral axis, maybe from this point, or maybe at this point where the shear force is maximum, or maybe any point along the web where we are having any particular shear force. So I would like to explain step by step. So I'm taking this small element from the web, and this element, this bottom is along the neutral axis. Just to explain you this, let me separate out these forces first, so that you will be able to understand. What I have done, I have taken a very small element along the neutral axis, and you can say that the height of this element may be dy and the thickness may be equal to dx, differential, very small. And at the bottom of this element, okay, this from this side, this is also continuous, this side is also continuous, this side is also continuous, because we have cut this material. So at the bottom, we can determine the horizontal shear stresses which are acting along by this formula. The x is equal to vq over ib, or va, so this I have written down, a prime into y bar, that's supposed to be, so that's supposed to be partial area above the layer and moment arm of that partial area above the neutral axis. So anyhow, we are able to determine. So you can convert this shear stress into shear force if you are multiplying this shear stress by the area, this area will be equal to dx, and you can consider that out of the plane dimension is 1, so you can say that this is equal to, because out of the plane dimension may be equal to 1. Just for your clarity, so I can say that this is equal to dx and into 1. So you have this force as a Vx force. So what do you think? Because on this element, we must have some reaction over here, some reaction here, and also reaction here to balance this free body diagram for element. Because these are the continuous material, because we have cut. So what do you think? This element is balanced? No. Just to balance this force, which is acting in this direction, if we apply summation fx is equal to 0, so we must have a force, a balancing force, which must be acting on the top side. And what do you think? Is this element still balanced? Yes, summation fx is equal to 0, but rotational equilibrium is not balanced. For example, if I'm taking the moment about this corner is equal to 0, so this force is passing through this corner, so its moment will be 0. And this force tend to produce the moment in counterclockwise side. So it means that rotational equilibrium is not equal to 0 or balance. So these two forces, they are perfectly equal in magnitude and they are acting in opposite directions. So these are called as a couple. Just to balance this moment produced by this couple, we must have a resisting couple acting on this. We have some forces acting on here which are making the resisting couple or moment. They are inducing the balancing moment in clockwise side. So we must have these balancing force or this balancing couple which must produce the moment in clockwise direction to balance the moment produced by this couple. This means that these three forces, they are just produced to balance this one single force. So from here, again, I am letting you know, you will, I will just explaining that you will discuss this topic in detail in next semester. But anyhow, from this behavior, what we have concluded, whenever any horizontal force or shear force is acting at any point within our beam, The same point is also subjected to a transversal force which is equal in magnitude, because this force and this force, they are having same magnitude. So for example, this corner, if at this point a horizontal force is acting, so the same point will also be subjected to a transversal or vertical force which will have same magnitude. And this force is called as a complementary force or complementary stress. So you can discuss these vector in terms of forces or in terms of stresses. So if this arrow is acting in this type, so this arrow is also acting toward this corner. So either that they will be their tails they will meet at the corner, or their head they will meet at this corner. So it means that the center of web, this center, this center point of the web is subjected to these four forces points along the neutral axis, you can say. So the behavior of the forces will be like this. Okay, further, so this point is very small, a dot. You can say that this is a one point. So I can convert these two forces into a single force. For example, if this force is like this and this force is like this, so by using parallelogram, rule of parallelogram, so we will have a resultant of these two forces. So by using basic mechanics to make these forces simple, we can replace these two forces by their resultant force which is acting at 45 degree, because magnitude of the both forces same. So when I replace these two forces by this force, and similarly these two forces by this single force, so what will happen is mean that this element, okay, let me separate out these forces first, and also, so it's mean that this force system and this force system is same. So it's mean that because we have converted these two forces into their resultant force. So what will happen? It means that this element is subjected to diagonal tensile forces. When this web panel will be subjected to these resultant forces, so the web will tend to elongate in this direction. So when the web is tend to elongate, so it means that you can say that shape of this element, it will change to this dash diagram, or this diagram that I have shown by the dash line. So the rectangular, it will change to trapezium. So it means that the contraction will occur in later direction. So it means that when the contraction, the element is elongated or being elongating along the tensile forces, so at the same way, to make the volume equal, so the element will contract in later direction. So when it is contracting, it means that it is contracting due to the compressive forces. So our web will be subjected to these forces. So these are principal plane and these are plane of maximum shear, but I'm not going to explain what are the principal plane and plane of maximum shear. But I can say that this force system and this force system, they are equivalent. And effect of these forces and effect of these forces on this center point of the web or the web panel is same. You can say that these are the maybe 100 rupees note, and here we are having 250 rupees. So it means that the total effect of these forces and these forces will be equivalent. So it means that due to these shear forces, if we are converting into their equivalent system, so the web panel is subjected to tensile force in this direction and compressive force in this direction. So again, the web is very thin or cylinder. So it may buckle due to this compressive force in this direction. And the web panel will tend to elongate along this direction. So due to this behavior, the web will buckle like this. Here there is a one experimental picture of a tested plate welder. So when it is subjected to apply load, so here you can see that web buckle along this diagonal direction, and in this direction, the tension forces are developed, and in direction, the compressive forces are acting, due to which the web buckle perpendicular to the compressive force, and in this direction, the web is subjected to tensile force. So you can see the stretching. So this phenomena will only occur if we are providing the intermediate stiffness. So what I want to say, if we are not providing intermediate stiffness, then the web will buckle and we will have only the formula tau y area of the web into CV. But the experiment, they have suggested that if after buckling the tension is developing along the diagonal direction, if these tensile forces are being resisted or by some other type of the member, then we can improve the shear capacity or enhance shear capacity of web. So it means that the steel which is very strong in tension or stable, so we can still reserve tensile capacity along this direction. So the internal forces or these tensile forces which are produced in the web, if these are being balanced by some external member or by providing some by making some modification plate girder, then we can improve its capacity. So this tensile force, it can be balanced by providing the intermediate stiffness. So intermediate stiffness, when we are providing certain spacing, so what happens? So let's suppose if I am resolving this tensile force into two components. This tensile force, one component is the tau x. For example, you can say that tau x will be Ty. So it means that if we are somehow will be able to balance this horizontal component of this tensile force and vertical component of this tensile force by any means, so we can improve the shear capacity. So horizontal component is balanced by the normal forces in plane, and the vertical component acting upward, it is balanced or it is resisted by providing intermediate stiffness. So intermediate stiffness will have compressive force. So if we are providing intermediate stiffness, so intermediate stiffness, they resist the vertical component of this diagonal force which is developing in this slab, and the flanges, they are balancing the horizontal component of this tensile force which is developing in web. Okay, in this case, we are having extra shear strength available. So the phenomena in which this tensile force will develop in this plate girder is referred as a tension field action. So the mechanism that by which the tensile force which is being developed in the web after buckling is balanced by the intermediate stiffness and the flange is referred as tension action. So at the moment I have explained the behavior. Now we will read out the definition of tension. Again, this is very important, and sometimes I ask this question in quiz. So this tension field action or improvement of shear capacity due to development of this tensile forces will only develop if we are providing intermediate stiffness, and this strength will only be available when the web will buckle first. So when the web is not approaching to its buckling strength, then this tensile force will not develop in the web. So this is also referred as a post-buckling strength. So post-buckling strength or tension field action is only available when the web approaches to its buckling strength and we are providing intermediate stiffness. Okay, now we will study the exact definition. The produced diagonal compression causes the buckling of cylinder web. Even after this buckling, the girder does not fail due to shear if we are providing intermediate stiffness. That is that this buckled web can still carry tension in a perpendicular direction. Perpendicular direction means in this direction we are having compression, so buckling will occur along this section, but the in perpendicular to this compressive force, so our plate girder is subjected to tensile forces. So steel is very strong in tension. So the reason is that this buckled web still carry tension in a perpendicular direction and form a truss-like arrangement or configuration consisting of flanges as a top and bottom chord and web acting as a tension member and stiffener behave as a vertical member. So here actually we are going to use a truss analogy. Sometimes we also ask the question, what is the truss analogy in plate girder? So what is the truss analogy? If we are providing the intermediate stiffener in our plate girder, then after buckling when web is approaches to its buckling strength, so after the web buckle, tensile forces develop in the diagonal direction, and just to balance this tensile forces, the top flange and bottom flange, they behave as a top chord and bottom chord of truss, and the intermediate stiffener, they serve as vertical member of truss, and the diagonal strip of the plate girder, it behave as a diagonal truss member. So thus the capacity is increased, shear capacity is increased by tension field action or truss analogy. So what is the truss analogy or tension field action? After the web buckling, the top and bottom flange, they behave as a top chord of the truss member, and the stiffener, they behave as a vertical member, and the diagonal strip, they serve as a diagonal member. So shear strength present after buckling. Here, let me bold. Shear strength present after buckling, which is also referred as a post-buckling strength. This strength will only be available after buckling. When the web will not buckle, tension field action will not develop. After buckling of the web is called post-buckling strength. The phenomena during which this strength developed by the presence of truss-like configuration in plate girder with intermediate stiffener is called tension field action. The phenomena during which this strength develops presence of truss-like configuration is called tension field action. So I have already explained. So this gives better economy and provides a more realistic idea of actual strength of the plate. So it means that if we are having extra strength available, so instead of increasing the thickness of the web, we can consider that fraction of the strength which is contributed by tension field action. Tension field action is always developed when a girder with stiffener is loaded beyond initial buckling stage. So this is very important to learn. So tension field action will only develop in two cases. What two cases? Number one, if we are providing intermediate stiffener, and number two, if the web is loaded beyond its buckling value. If the web is not subjected to its buckling value, because tension field action will only develop when the web will buckle. And when the web will buckle and perpendicular to the buckling direction, the tension or tensile forces will develop. Thus, during tension field action, a diagonal strip of web behave or act like a diagonal member of truss cord. The stiffener prevents flanges from coming closer to each other, and flange prevent the stiffener from moving toward each other. So what does it mean? So the flanges they will not let uh, to reduce the web thickness, web height, and also the stiffness. They will also resist uh, the shorting, the reduction of the dimension or the change of shape of this web panel. So if we are not providing intermediate stiffness, then the buckling or deformed shape of web will be likely. Intermediate stiffness, which before initial buckling were assumed to resist no load, will resist compression load after web buckling and will serve as a compression vertical of truss. So what does it mean? It is very important to understand. Intermediate stiffeners, they will only active or they will only become active once the web will buckle. So before the web buckling, no compressive forces develop in intermediate stiffener. So they become only active once the web buckle, and when the web will buckle, then that tensile forces will develop in web panel, which must be resisted by the intermediate stiffener and flanges. With tension field action, a web may resist shear equal to 2 or 3 times that present at initial buckling. So what does it mean? He says that tension field action contribute the shear capacity almost 2 to 3 times more than web buckling strength. So what does it mean? If let's suppose this is constant, this CV value is the fraction of the strength available due to web buckling alone. And prime is the strength enhancement due to the presence of intermediate stiffness. So actually CV it is the coefficient which is letting us know the shear strength of the web alone, buckling strength of web alone. And CV prime is the factor which is letting us know the contribution of tension field action. So if when we are solving the example, you will see that CV prime value will be almost 2 to 3 times more than CV value. If CV value it is zero point 0.2, then CV prime value will be maybe 0.6. Or let's suppose if CV value is 2, then CV prime value will be maybe 3, sorry 6. So we can have an idea. So when we are solving the numericals, so I will repeat it again. So ultimate shear that a panel of the web between adjacent can withstand is equal to shear strength, buckling strength of the web alone plus shear strength contributed by tension field action. So I have just explained. The amount of tension field action is depending upon proportioning of panel. Proportioning of panel means what is the spacing of the intermediate stiffness. Closer are the stiffness or less is the A value, more will be tension field action. The resulting deflection may increase to several times the value estimated by usual deflection theory. So actually he's saying that when we are achieving the shear capacity or we are improving the shear capacity by tension field action, because tension field action will only be available when the web, and when the web will buckle, it means that it will undergoing large vertical deflection. So after that, when the tension field action develops, when we are increasing the load, the failure will only occur once the yielding at the top line, at the junction of the top line, and at this at the bottom line will yield. So here is some maybe some diagram from some study or numerical study on computer software. So we have determined the you can say that the ultimate load carrying capacity of two plate girders. So in one plate girder, we have used the intermediate stiffness, maybe 1, 2, and 3, along the stiffness at the end, which are the bearing stiffness. So we are having load carrying capacity like this. So ultimate load carrying capacity is 800, and after the web buckle, we still have some reserve capacity. In another plate girder, when we tested without this stiffener, so its ultimate capacity is less, and also after buckling, so capacity is reduced sharply. So this is without tension field action, and this is with tension field action. And here, that is the evidence from this computer simulation. So when we apply the load, so when the web will buckle, so here you can see this red zone. So tensile forces, they are developed in diagonal direction, and web buckle in this direction. So in this direction we are having compressive forces, and this red strip, it indicates that this strip or this diagonal direction is subjected to some tensile forces in this direction. And these tensile forces which are developing in this direction, diagonal directions, are being balanced by the compressive forces in this stiffness and horizontal forces in this line. So the member will only fail when the top line at this junction will subject it to yield stress, or it will yield. Okay, so what is the CV and CV prime value? I have already shown you this formula. So the total shear strength is the summation of the shear strength provided by the web buckling and strength provided by or contributed by tension field action. So this is the shear coefficient for depending upon web buckling alone, and this is the shear coefficient or the shear strength enhancement factor due to tension field action. So we will study their proper definition. CV called shear coefficient without tension field action and stiffness, or CV value is the shear coefficient or the shear strength parameter, shear strength provided by web alone. So called shear coefficient without tension field action and stiffness. So it is the ratio of critical web stress to shear yield stress of web material. So CV is the ratio between critical mean buckling shear strength over yielding shear strength. Or in other words, CV value is used to convert the yield strength to the buckling strength. So CV value will always be less than 1. So this is the parameter that is let us know that at what percentage of the shear yielding the web is buckling. So fraction of shear strength available due to web alone or buckling strength of web alone. This is a parameter that is used to determine the buckling strength of web alone with respect to shear yield strength, shear yield strength of the web compact. So as compared to the shear yield strength of the web, how much percentage or fraction of web buckling strength is available. And what is CV prime? That is additional CV value for tension field action due to stiffness alone. So let me have it. Or fraction of shear strength available with respect to shear yield strength of web due to stiffener producing tension field action. How much extra strength as compared to the yield strength is available due to tension field action. So Kv is web buckling coefficient. Okay, next question is that how we can determine Cv and Cv prime value. So before explaining this, so I think it is better to have the break at this time. So please raise the hand all the students who are present at the moment. There are total 36 students present. Please raise your hand. So it's mean that at this point maybe only out of 36, maybe 18 students they are present. So Amir Bashir, Ayan, Ayan, I don't know, maybe Faisal or Farouk, Haris, Miss Laiba, Salihan Naim, Shahzeb Hamid, and Zain Ali. So I am capturing the picture of this.
Sir, I'm here. My hand raise option is not working.
Okay, no problem. I have marked yours. So here I am having a break of 15 minutes. So I will start exactly 11:15. So okay, who was the student who was responding? क्या नाम था आपका स्टूडेंट का?
Azib.
Shazib. अच्छा. Could you let me know what are the function of intermediate stiffness? Just explain me. What is the difference of bearing stiffener and intermediate stiffener? Because you was present. Yes. Yes, Shazib. You do not know. So, as we have discussed previously, so I told you that when the web will buckle and we are providing intermediate stiffener. So a bearing stiffener, it will also serve as intermediate stiffener. So when a web panel is buckling and it buckles due to the compressive forces which are developing this direction, and after buckling, the tensile force will develop along this diagonal direction. So we can consider a web strip of uniform thickness which is subjected to tensile forces. If these tensile forces which can be balanced, that we are balancing the horizontal component of these tensile forces or the tensile force which is developing in this strip by the resistance offered by flange, and the vertical component of this tensile force is being balanced by the compressive forces which are developed in intermediate stiffener. So after that, when any of this, when this applied stress, when the stresses in this stiffener or in this flange due to these resisting forces will become more than yielding of material, then the failure will occur. So if these stresses are less than yield stress, it means that they will be capable to resist or to balance these tensile forces. So they are enhancing or improving shear strength that we have already discussed. So at the junction of intermediate stiffener and flange, equilibrium requires an axial tension to develop in flange of the adjacent panel. When no such flange is available as an end panel, the tension field action cannot adequately develop. So tension field action can only develop when the flange is sufficiently thick and we are providing intermediate stiffness. Because if flange is unable to balance horizontal component of this tensile force, then tension field action will not be balanced or developed. So AISC specification therefore consider that only buckling strength is available without tension field action. So if the flange they are thin or we are not providing intermediate stiffness, then we will not have the strength contributed by tension field action. So the capacity will only be governed by the buckling strength of web. And how we can compute the total shear capacity? Total shear capacity is computed by a fraction of the strength contributed by the web buckling alone and fraction of the strength contributed by tension field action, which can be determined by computing CV and CV prime value respectively. So if we are given the design of plate girder, design of plate girder means that we know the flange size and the web size, and also spacing of stiffener and the size of stiffener is given, then we can determine the total shear resistance or the shear capacity of web with and without tension field action. So how we can compute CV value? So CV value is based upon three conditions. Just like I told you that our web, our plate girder, it may be compact depending upon flange compactness, depending upon lateral torsion buckling, and similarly based upon web local buckling. So if you can see that we are having three different formula, just I'm giving you the analogy. We are having three different expressions to compute CV value. For example, if our web is compact, so in that case, if height of the web over thickness of the web ratio is less than this parameter, 1.1 under root kV into E over Fy. So you can consider that this is the lambda p value for the web of plate girder. Then if our web is compact, then web will not buckle. It will only fail due to shear yielding. In that case, CV value will be equal to 1 or buckling strength will be equal to yield value, shear yield value. And if height of the web over thickness of the web ratio is more than this parameter, but less than 1.37 under kV over kV into E over Fy, then we may consider that our web is non-compact or it is undergoing inelastic buckling. In that case, CV value will be determined by this equation 3, which is 1.1 time under root kV into E over Fy divided by lambda W. Lambda W is the ratio between height of the web to the thickness of web. And if lambda W means aspect ratio of web, height of the web over thickness of the web is more than 1.37 under kV into E over Fy, then we need to use equation number 4 to compute CV value. So CV value can be computed by using any of these three expressions. Actually, in order to check the compactness of of the web or height of the web over thickness of the web ratio, we need KV value. So how to compute KV value? First of all, what is KV? That is the web plate buckling coefficient. So KV value is the web plate buckling coefficient, which is depending upon the panel size or the aspect ratio of web. So this KV value will be equal to 5, or when we are not providing intermediate stiffness. If we are not providing transverse or intermediate stiffness, then KV value will be equal to 5. Or if height of the web over thickness of the web ratio is also less than 260, so in both cases KV value is equal to 5. But when we are providing the stiffness, then we need to compute KV value by this expression. 5 plus 5 divided by A over H ratio. This means that KV value is the function of spacing of stiffness and height of the web. So lesser will be the spacing, more will be the KV value. Because if A will be larger, so we will have this larger component. So 5 divided by a larger value will have the lesser answer. So KV value is the function of spacing of stiffness. A is the spacing of stiffness. So in other words, we can say that KV value, if it is a function of spacing of stiffness, and then H over TW ratio is need to be compared with this parameter, which is also the function of KV value. So depending upon this condition and elastic buckling or the cylinder web, we are having two different CV formulas. Because CV value is also directly proportional to the KV value. So what we can say that CV value is also to a certain extent is the function of spacing of stiffness. Because KV value is 5 if we are not providing intermediate stiffness. So minimum value of KV will be 5. So KV value will be larger if we are intermediate stiffness. So for unstiffened web, K value will be equal to 5. So let me make it KV. Sometimes actually we are providing the stiffness, but spacing of the stiffener is very large. So if the spacing of stiffener is very large, so tension field action will not develop. So tension field action will not develop if A over H ratio is more than 3. More than 3 means that spacing of stiffener is more than 3 times of height of plate girder. Or if A over H ratio is more than the square of 260 over lambda W ratio. So we will satisfy this condition we are designing plate girder. And the formula for CV prime will be this one, equation 6, and it is the function of CV value and A over H ratio. Again, CV prime is the fraction of the strength available due to tension field action. So this formula CV prime only applicable if A over H ratio is less than 3. First, if we are providing stiffener and spacing of stiffener is less than 3 times of the height of plate welder, and also A over H ratio is more than 260 over height of the web over thickness of the web ratio square. Okay, next. Actually, the main important thing is to compute the spacing of stiffener. And how we are going to compute the spacing of stiffener, I will explain in the design procedure. But next, if we have selected the spacing, then what would be the size of intermediate stiffener? So intermediate stiffeners, when we are providing, for example, on the both sides or maybe on one side, so they must have sufficient stiffness about the out of plane direction. It means that when the web is buckling, so stiffener they should have sufficient moment of inertia so that they cannot buckle about the center of web. So how we can compute this? So we are computing the moment of inertia about the center of the web. And this moment of inertia should be equal to or more than this value. So moment of inertia of stiffener, intermediate stiffener about the center of web should be equal to or more than this particular parameter, which is equal to J B into thickness of web cube. What is the B value? B is smaller of A and H. Again, let me show you what is the A and what is the H. A is the spacing of stiffener and H is the height of plate girder or depth of plate girder. So A value should be less than 3 times of H. So A should not be more than 3 times of height of plate girder. So lesser value in most of the cases H. So B value will be in most of the cases will be H value. The lesser or the least dimension of web panel between two stiffeners. So whatever is the lesser out of H and A, that will be the B value that we are going to use in this equation. And what is the J value? J value is computed by this expression. So J is equal to 2.5 divided by A over H ratio square minus 2. And this value should not be less than 0.5. So this value is always equal to or more than 0.5. Okay, when you will compute the J value from here, you will have some numerical value. And when you will substitute the J value, you will have B and thickness of the web cube. So that is the minimum moment of inertia required for the intermediate stiffness. And then what we can do, we can compare this moment of inertia by this its actual expression. So we can compute the moment of inertia about this center of web. So actually, this expression is equal to so if I'm taking the moment of inertia of these two stiffeners, so if B is the width of this stiffener, one stiffener, and TST is the thickness of one stiffener. The total width of two stiffener will be equal to BST plus thickness of web plus this BST. So total depth of two stiffener along with the thickness of the web will be equal to 2 times of the BST plus thickness of web. And this thickness will be equal to TST. So moment of inertia will be equal to B into D cube divided by 12. So B value is the thickness and depth is equal to 2 times of the B value. One B value is 1B and thickness of web. But for simplification, we ignore this thickness of web. For simple calculation, we ignore this thickness of the web, so we are having this simple formula. So this is the moment of inertia of intermediate stiffener about center of web. So if you are using two stiffener you are using stiffener in pair, then you will have this expression. But if you are providing a single stiffener only on the one side, then you need to deduct this two, because total thickness of the stiffener about this center will be B. And then if you are computing the moment of inertia of one stiffener about its base, so this formula will be 3, because you are supposed to compute the moment of inertia of stiffener, single stiffener about its base. The moment of inertia of rectangular about centroid is B d cube divided by 12, and moment of inertia of stiffness about its base will be B d cube divided by 3. But anyhow, this is the expression for moment of inertia of a pair of intermediate stiffness. So we are equating this expression with JB into thickness of web cube. So because IST minimum value should be equal to. So from here, we already know this parameter. So if we know, if we fix the thickness, we can determine the B value. Or if you can fix the B value, we can determine thickness. Okay, now this equation number 9, actually this equation number 9 has been eliminated or discarded. This equation number 9 is no more being recommended by AISC. In the latest code, this equation is not used. So previously, this equation was used to determine minimum area of stiffness. So anyhow, I will explain what is this equation. So minimum area of this stiffness we use to compute by this expression. Fy is the yield strength of web. Fyst yield strength of stiffness. ds is the distribution factor, which accounts for eccentric loading. So if we are using the stiffener in pair on both sides, then ds value equal to 1. If we are using this stiffener at a single angle, only one side, ds value is 1.8 and ds value is 2.4 if we are using intermediate stiffener as a single plate. CV value we have already determined, height of the web is already known, thickness of the web is also known. So what is the required shear strength at location of stiffness, and Vs is the available shear strength. Actually, what does it mean? It means that Vc is the shear strength of web alone, and Vr is the applied shear force. So how I can explain? Let's suppose I want to provide a stiffener here at this point. So what is applied shear? 1590. So VR is required shear strength, which is applied shear force, which we are getting from shear force diagram. And Vs is available. Available means the shear strength provided by web alone. If web alone is providing shear strength 519, it means that we must increase the shear strength by 1000 value, another 1000 value. So, but anyhow, this equation is no more being used. Okay, so next thing is that from here, in this expression, we know this JB of the web cube. This is one numerical value because thickness of the web is known. B is lesser out of A and B. J we are determining from here. So actually, this equation we are having two unknowns, one TST, one BST. So we are solving this equation and this equation simultaneously. So AISC says that B width B over thickness ratio of the stiffener should be less than equal to 0.56 under root E over Fy, which is 15.844836 days. Please correct this value in your book. In your book, this value is written as a 28 point something, which is misprinted. So actual value is 15.84. Please also correct in your book. So if I'm fixing B over ST value 15.84, or BST will be equal to 15.84 time of thickness of stiffener. So by using solving this equation and this equation simultaneously, we can compute the B and T value of stiffness. After that, we are having another check. So we are having an additional check for the moment of inertia. So total moment of inertia of stiffener should be more than this parameter. So in this parameter, what is IST1? IST1 is just this value that we are computing by this expression. So IST1, we are computing the moment of inertia of stiffener when we actually know the thickness of stiffener and width of the stiffener. So we are ignoring this thickness of web. So if this side is more, so we don't need to revise the size of stiffener. But if this portion is lesser than IST value, we need to determine. And what is IST2? IST2 is determined by this formula, which is h power 4 into rho st1 power 1.3. What is rho st? That is the ratio between yield strength of the web to the yield strength of stiffener. If we are using same steel in stiffener and also in web, then rho value will be equal to 1. And this complete parameter will be equal to 1. FYW yield strength of the web over E value. For 836 steel, Fy is 250 megapascal, E value is 200,000 megapascal, and rho st is equal to 1. If we simplify this equation, that will be equal to 1.105 under exponent minus 6 into h4. And what is this value? So IST2 is the minimum moment of inertia of transverse stiffener for development of full resistance against both web shear buckling and web tension field action. So this is the minimum moment of inertia required to resist the web buckling and also tension field action. And what is the IST1? That is the moment of inertia of stiffener about the center line for stiffener in pair about the face in contact with web for single stiffener. So it means that that is the moment of inertia, minimum moment of inertia provided by the stiffener just to resist the web buckling. And this is the minimum moment of inertia required to resist both web buckling and tension field action. So ISTI and how these values are determined, I have already explained. And what is this VR value? VR is lesser of required VU in adjacent panel. And VC1 smaller of VN in adjacent web panel using CV only. And VC2 smaller of VN in the adjacent panel web panel using both CV and CV prime. Okay, let me explain from some diagram. Let me compare, let me copy, and similarly, I need to copy the web panel also, just to make this diagram more simple. And let me also copy this diagram maybe here. Yes, I need to make this diagram more bigger, and this diagram small. Anyhow, this would be fine. So what I want to explain, let's suppose we want to decide the intermediate stiffness now, and intermediate stiffness, let's suppose this bearing stiffness is also served as intermediate stiffness, and one stiffness I am providing over here, and one stiffness, let's suppose, and this is a bearing stiffness I am having, and one stiffness may be in the center, and one stiffness may be over here. What I want to explain, if I want to design this intermediate stiffness, this one. So this intermediate stiffness is having this web panel and also this web panel. So what will be the VR? VR is lesser of required VU in adjacent panel. Lesser. Lesser mean, where I have gone? in this web panel, because if I'm moving, so at this edge we are having shear force 1519. So what will be the shear force at this point? What is the maximum shear force in this panel with reference to applied? So the maximum shear force within this panel will be this 1519. And in this panel, the maximum shear force is this one and minimum is this one. So this panel is subjected to lesser shear force, which is at this junction. So VR value will be what is the minimum applied shear in adjacent panel or in any one panel on the both sides. So that will be the shear force at this junction, because at this web panel is subjected to maximum shear 1519, and this web panel is subjected to maximum shear just at this junction. So the lesser value will be in this second panel. So VR will be whatever is the shear force at this junction. So we shall determine when designing. And similarly, what is the VC1 is smaller of VN in adjacent panel using CV only. So here we need to check whether this web panel, okay, I'm designing this stiffener, okay. So we are having one panel on one side and one panel on the other side. So you need to check which panel on either side is having less buckling strength, web buckling, without tension field action. So whichever panel is having less web buckling strength without tension field action, that is VC1. Similarly, you need to determine the shear capacity of this web panel and this web panel, both with tension field action also. So which web panel will have the web buckling, the shear strength, including tension field action lesser, that will be VC2. So if this panel is having lesser shear capacity in tension field action, then VC value will be based upon this panel. So I will elaborate more when we are discussing design examples. So VC2 smaller of VN in adjacent panel. Adjacent means we are having two panels on both sides of stiffener. So which panel is having less shear capacity, including tangent field action, and which web panel on either side is having the shear capacity excluding tangent field action. So that is the expression that we need to satisfy over here. And the last thing that we are going to discuss, the weld between transverse stiffener and web must be terminated not less than 4 to 6 times of thickness of the web near the toe to the web to flange. So this is this. So actually, bearing stiffener, when we provide thoroughly between two top flange to the bottom flange. But the intermediate flange, intermediate stiffener, they are starting from the bottom face of top flange, and we cut or discontinue at a certain distance from the bottom flange. So we provide a gap between bottom flange and this stiffener, and gap is between 4 times thickness of the web to the 6 times of thickness of the web. Why we provide this gap, I will explain in my next lecture, because we want to avoid the stress triaxiality. We want the three-dimensional stresses at this bottom junction, which may cause cracking at this bottom flange. So how we can avoid this? So I shall explain. And similarly, along this, the we connect the stiffener with the flange by continuous weld, and we connect the flange plate with the web by providing the intermittent weld. So we provide intermittent weld with some spacing. And specification are for intermittent weld are also mentioned here. If bolts connecting stiffener to the girder web should have maximum spacing of 305 mm on center. If we are connecting the stiffener with the help of fastener, for example, a stiffener may be angle section with the web, then maximum spacing of the fastener should not be more than 305. And clear distance between intermittent fitted weld should not be more than 16 times the web thickness and 250. If we are providing intermittent weld, then the clear distance between intermittent weld should not be more than 16 times of thickness of the web or 250, whichever is the lesser. So when we detail, I will explain it again. So I will stop here. So next time when we will start, I will explain the design flow chart for the intermediate stiffener design, and we shall start solving the example number 1 also. So the example number 2. So at the moment, I'm going to download the tenders. If anyone is having question, please raise the hand. Yes, Jawad Ahmed, what is your question?
सर वो आपने सिलेबस अभी तक नहीं बताया।
सिलेबस मैंने कब का बताया हुआ है
सर, रिपीट कर दें एक दफा।
for midterm, just before the built up section design, lacing design से पहले 3.8 से पहले. So for the midterm, you will have one question from the design part. What will be design part? Maybe table of forces, purlin design, and roof sheeting design. You are expecting one question from in this portion, and then tension member design, chapter number 1, design philosophy and design behavior, and compression member before built up member design. Built up member with lacing before that part. So you got it? CR, class CR.
मतलब चैप्टर नंबर 7, 1, 2 और 3 हाफ।
हाँ जी, चैप्टर नंबर 7 पूरा जो हमने लैब में किया है, ठीक है? And that include table of forces, roof sheet design, and panel design. And chapter number 1 complete, chapter number 2 tension member design, and chapter number 3 compression member half, just before built up member design with lacing. You understand?
Yes, sir.
So any other question?
सर मतलब बिल्ट अप मेंबर एक्सक्लूडेड है ना, वो इंक्लूड तो नहीं होगा?
स्टे प्लेट वाला इंक्लूडेड है, बट लेसिंग वाला एक्सक्लूडेड है।
चलिए ठीक हो गया सर।
सर रिपोर्ट का भी बता दें।
प्लेट वाला इंक्लूड बिल्ट अप मेंबर विद लेसिंग इज रिपोर्ट का मैंने कब का बताया हुआ है। रिपोर्ट का आपको
एक
प्रेजेंट से सीआर
सर साइकोमोटर वो
यस साइकोमोटर का क्या पूछ रहे हो? यस हसन व्हाट इज दैट? हसन प्लीज आस्क द क्वेश्चन। ओके जवाद यस, जिसने क्वेश्चन पूछना है फर्स्ट रेज दी हैंड। यस बिलाल मिर्जा, व्हाट इज योर क्वेश्चन?
सर तो इससे सर ये बताना था कि वो सीआर ने मैसेज लीव किया आपके लिए, वो क्लास लीव कर गया था।
कोई बात नहीं यार, तुम आगे कौन से टेंटेटिव बोलते हो, कोई समझ नहीं आता। आते सर मैं वैसे भी कुछ नहीं है। ओके रिपोर्ट का ना फॉर्मेट मैंने शेयर किया हुआ है। व्हेन यू आर कमिंग आफ्टर मिड टर्म फॉर साइकोमोटर, so you need to submit the report on very first day. वो रिपोर्ट का फॉर्मेट हमने डिटेल में डिस्कस किया हुआ है। आई हैव डिस्कस इन डिटेल So you must have your lab report complete. It must include panel load calculation, purlin design, roof sheeting design, design of all members, all connection design. Complete lab report must be submitted. So in the first week of psychomotor, I will explain how to draw the truss sheet, and then in 2 turns or in 2 class sessions, you need to draw the truss sheet in lab or in drawing class.